Okay, so well, let me continue the definition of deformation spaces. So the third one. So in a dimension 2, the third one was Teichmüller's original definition of Teichmüller space. And so it's based on the theory of the quasi-conformal maps or Teichmüller maps. So we try to generalize it to dimension 3. So we start from some point in a Teichmüller space X. And then, as I defined in a previous one, it's just a set of, it's just an equivalence class of the set of pairs sigma and f, and the sigma is a Riemann surface and the f is homomorphism. And it's also so because in a dimension 2, the three definitions are equivalent. So corresponding to that point in the Teichmüller space, you have a representation of pi 1 of S to PSL to R, which is well defined up to conjugacy. Now, we would like to generalize it to dimension 3. We'd like to change the PSL to R to PSL to C. But PSL to R is evidently a subgroup of PSL to C. PS to R is a subgroup of PS to C. So this representation, which is called actually, this is called Fuchsian representation, is also regarded as a representation into PSL to C. Okay. Actually, I haven't defined the Kleinian group yet, but so let me just tell you that Kleinian group is just a discrete subgroup of PSL to C. So if you change the C to R, then it's called a Fuchsian group. Okay, discrete subgroup of PSL to R is called a Fuchsian group. So now, if you deform, or if you consider the space of the representation within PSL to R, that makes a Teichmüller space. But here we'd like to consider the deformation of this representation in a PSL to C. Okay. And the PSL to C is this was orientation preserving isometries of the H3, but at the same time it's just a transformation like this. So it's a linear fractional transformation. It's a transformation on our. So this is regarded as a transformation on the Riemann sphere, which is a one-point compactification of the complex plane. And we impose the condition that AD minus BC is equal to 1 and divided by plus minus I, as usual. Plus minus I means yeah. Then that is PS. That is equal to the PSL to C, and so now we are going to deform this representation by a quasi-conformal map, using quasi-conformal map. So if you have another representation of pi 1 of s to PSL to C, which is faithful and discrete, so it's said to be quasi-conformal deformation of phi if and only if there exists an orientation preserving homeomorphism from the Riemann sphere to Riemann sphere, which should be written as H, such that H, the first of that, H is a quasi-conformal map. That is the dilatation is finite. Or equivalently, the Beltrami coefficient, the norm of the essential norm of the Beltrami differential is less than 1. And so for any point in a Riemann sphere and any element in a pi 1 of s, so this is equal to the conjugation of the phi g by h. That means that is something like that. So this was a Fuchsian representation here, and psi is another representation to PSL2C, and if PSL2C, the representation into PSL2C is obtained by conjugating phi using this homeomorphism, which is assumed to be quasi-conformal, then psi is said to be quasi-conformal deformation of phi. So is it clear? Any questions about the definition here?
There, the equation is the Beltrami coefficient in each point is less than 1.
This one?
Yes.
No? This one? This is so it's an essential sup norm. So except for so if you ignore the major zero part, then the supremum is less than 1. So it's a sup norm. So wait. So this is equivalent to saying that the dilatation is finite. Okay. So this should be the quasi-conformal deformation, and we would like to consider the space of the quasi-conformal deformation of as Fuchsian representation. And actually, there is a parametrization of this space, and that can be done by using the theory of the Bayes. So it's called the Bayes simultaneous uniformization. So we start from Fuchsian representation. So it's a representation pi 1 as PSL to R. And next we define something called a limit set. So this is called a limit set of phi, or phi of pi 1 of S. Probably this should be the correct notation, but it's defined to be a closure of the point in Riemann sphere, which is fixed by an element in a pi of pi 1s. So it's exists in phi gamma z is z. So you consider the point fixed by some element, which is, well, that is not the identity.
So you're still considering a PSL to R?
It's a PSL to R. It's a representation of PSL to R, not the PSL to C. This definition works for any Kleinian group, but at the moment we are considering the PSL to a representation of PSL to R. Okay. So in our example here, so if you consider that one, then this is equal to the 1-point compactification of R, real axis. Okay, this should be the exercise. So now, if you just draw a picture of the Riemann sphere, you have a real axis somewhere there. Okay. So this should be real axis. This should be the imaginary axis. And so you have two disks here. So the D plus corresponds to the point where the imaginary coordinate is greater than 0, positive, and then this is the negative imaginary. This is a point where the imaginary part is negative, and the point at the infinity line is there. Okay. So 0 is somewhere like there. Okay. So you have a picture like this. So outside this kind of set, phi pi 1s acts properly discontinuously. Okay. Actually, the action of the pi 1 of s, or phi of pi 1 of s, on D plus or D1 can be identified with the action of phi of pi 1 of s on H2. So this can be identified, the real axis can be identified with the circle at the infinity of the Poincare model of the hyperbolic plane, and then the action here is identified with the action on the H2. So Any other questions? So now, so what this argument shows is that you have a parameterization of quasi-conformal deformations of psi, no, not psi, phi, quasi-conformal deformations of phi modulo conjugacy. So you have a parameterization here. So it's a product of two Teichmüller spaces. So Ts times Ts, but because the identification is with orientation reversing for the second one, so you just put bar on there. So you have a homeomorphism here. So it's a Euclidean space of dimension 12G minus 12. Okay. And it's often written like this. So it's the symbol for this space is usually QF, meaning the quasi-Fuchsian. So again, we put the qualifier quasi. So it's called the quasi-Fuchsian space. So this should be the generalization of the Thurston's original definition of Teichmüller space. So you consider the quasi-conformal deformation of the original of a fixed representation, Fuchsian representation, and you get some kind of the space. So the dimension was doubled as you change the PSA to R to PSA to C. Okay. So now, so we have three spaces, HS, and AH of S, and QF of S. Okay. So in dimension 2, these three are the same. So now we turn to look at the relation between these three in the case of dimension 3. So did I put the 3 here? Not here, probably. I'm not sure. No. Okay. So we first look at the relation between H of S and AH of S. So H of S is the space of the hyperbolic structures on S times interval, and AH of S was the space of the representation of pi 1 of S into PS to C. Okay. So there's a map from H of S to H of S. That it's a natural, it's a holonomy. So if you have a hyperbolic metallic, then it's universal cover. Universal cover is just S tilde times interval has a hyperbolic metallic. And this is this is simply connected, hyperbolic, complete hyperbolic space. So that should be isometric to H3 standard hyperbolic space. Okay? And the pi 1 of this one is just a pi 1 of S. So pi 1 of S acts there by isometries. Okay? So this gives a faithful discrete representation of pi 1 of S to the group of isometries of the H3, that is the PSA to C. So this gives a map from HS to AH of S. And it's easy to see this map is injective. So this is easy exercise. Fact is that this map is also surjective. This is not easy at all. First of all, so if you have a faithful discrete representation of a pi 1 of S into a PS to C, so suppose you have a, because PS2C is a group of the orientation preserving isometries of H3, you can consider the quotient. Okay? Okay. So this is a hyperbolic 3 manifold, and pi 1 of it, this one, pi 1 of this one, is evidently, so because this is a coupling translation, it's evidently the isomorphic to pi 1 of S. Okay? Psi is injective, so that it's just pi 1 of S. So you have a hyperbolic 3 manifold whose fundamental group is pi 1 of S. Okay, so do you know that something called aspherical space or aspherical manifold?
People who took my class last night.
So, because this is a quotient of H3, the only, so there's something called the homotopy groups in which is a generalization of a fundamental group. And because this is it's universal coverage H3, there's no higher homotopy groups for this space. So it has it is something called aspherical. So it has a fundamental group which is isomorphic to the fundamental group of S, and there's no higher homotopy groups. And then in that case there is something called a Whitehead theorem. Probably nobody knows Whitehead. So two aspherical well, CW complexes. Well, so in this case, the manifold. So the two spherical manifolds are homotopy equivalent if and only if their fundamental groups are isomorphic. So this implies H3 over this is homotopy equivalent to S. So you have a 3 manifold which is homotopy equivalent to S. So that means it's homotopy equivalent to S times interval. Okay? But this doesn't imply in general that this manifold is homeomorphic to S times interval. Why? Because you don't know if it's so if the manifold is compact and if you have a 3 manifold which is compact and homotopy equivalent to closed surface S, then it must be homeomorphic to S times interval. But this manifold is not compact. This is an open 3 manifold. In this case, we don't know if it's so in general, you don't know if it's homeomorphic to the interior of some compact 3 manifold. Any questions to that? So I'm talking about something very difficult. So or something very subtle. So you can ask anything if you are not satisfied with this explanation. It's yeah.
When you use Phi-test theorem, at least I know what Phi-test theorem statement is when xy is a very space-like CW complex and fg are mapped between x and y. They induce same homomorphism in every higher homotopy groups. Yeah. Then f and g are homotopy to each other. But in that statement, we know that only the
yeah. So except for pi 1, all the other homotopy groups are 0.
But we can deduce their homotopy equivalence even without any. We don't know there is any map that induces isomorphism between.
Okay. Well, actually, we know that there is so because you have a action of pi 1 of S there. So you have a inclusion of S into that, which implies, which induces this isomorphism. So you have a map inducing isomorphism between pi 1 of S and H3 over pi 1 of S. It's easy to see that if you check the fix a generator and so take it to the generator there and then you have a relation coming from the product of the commutator and that should be 0 here. So you just you can extend the map to the so you have a map. So this map induces isomorphism between the fundamental groups. And also the isomorphism between the higher homotopy groups because they are all 0.
A priori, we don't know if they're embedding. A priori, we don't know if this is embedding. It's just that.
This is not embedding at all. This is not embedding at all. Just a map, just a continuous map. Continuous map inducing the isomorphism between the fundamental group.
How to define that? What is the definition?
So you have a generator system of pi 1. Okay. So corresponding to that, you have you have a map. You can map it to so that this isomorphism is realized. So you have a isomorphism between them. So there is image of this loop, and that loop. So all the loops can be mapped there. And the relation should be preserved because this is a isomorphism. Okay. Any other questions? Okay. So what I said is, if you know that there's a compactification of this one, I mean, if you have a compact three manifold whose interior is homeomorphic to this one, then we know that it's homeomorphic to the S times interval. But in general, there are many examples for which the compactification doesn't exist. So what proved by Bonahome is this. So for it, actually compactification exists. So for any psi in H of S, H3 over pi 1 of S can be compactified, and it's homeomorphic to S times sample interval. So his proof relies on the technique invented by Thurston. So this is a really difficult theorem, and if I try to prove that, then I would need more than 10 hours. So I'm not going with that. But so if you are interested in this theorem, you can read his paper. But I should say it's written in French, so you are supposed to read French to understand that. But anyway, so it's very famous and it's a very good result. So so this implies now. This is surjective. So we know that AHS and the H of S they are the same. Okay. Now I turn to the third one, QF of S. So QF of S is defined to be quasi-conformal deformation of phi. So you have some representation which is obtained as a conjugate of the some fixed friction representation by a quasi-conformal homeomorphism. So you have some representation of pi 1 of S into a PSL2C. So these points can be regarded as a point in the H of S naturally. But actually they do not coincide. So this is not empty. So this was shown by bears or musket, etc. Actually, this contains uncountably many points. So I have 10 minutes left.
To take a closure and look at everything?
Yeah, so that's what I'm going to say next. So the theorem. So for this special case, it's a Bloch and Blomberg. It's a part of something called the density theorem. So in general, it's called the Beer-Sullivan-Thurston density theorem. But in this special case, it's just Beer's density theorem. It's known that this is although the AHS doesn't coincide with QF of S, the closure of QF of S is AH of S. And also there's a theorem by Sullivan saying that the interior of AH of S is a QF of S. So what do we mean by interior? So the interior makes sense only when you embed AHS somewhere. But this interior is taken inside the space of the representations modulo conjugacy. Okay. Now in the remaining. Yep.
You know that AHC is homomorphic to some Euclidean space when there is
QF is homomorphic to Euclidean space. AH of S is not homomorphic to.
We have some easy description of the AH.
No. It's very complicated. Actually, it's not a manifold. So let me just say, this is a theorem by McMahon. H of S is not a manifold. Okay, any other questions? So I have only 7 minutes, so maybe I'm just going to talk about what I'm dealing with tomorrow. So this story was about the S times interval. So of course you can consider other three manifolds. And well, as I said, S times interval is the most it's not trivial, but it's the simplest actually case. So let me turn to more general cases. So in general, what we have to consider is a compact three manifold which is compact orientable, which satisfies the two conditions. If one condition is irreducible, and then the second condition is heteroidal. So for hyperbolic three manifold, well, to consider the hyperbolic structures, we have to impose the two conditions. So let me tell you what they mean. So the first, the M irreducible if any embedded sphere in M bounds a three ball. So, well, if you like to look at the three manifold which is not irreducible, which is said to be reducible, then you just take any three manifold which is not a sphere and consider the connected sum. Then you get three manifold which is reducible. So otherwise you have otherwise, except for the S2 cross S1, actually, you have a reducible three manifold. So it's a kind of the prime numbers in the theory of the, so prime numbers is numbers so generating all the other numbers by considering the multiplication. So in the theory of three manifold, if you consider the irreducible three manifold, you can construct any other manifold by just considering the connected sum. So that's the first assumption, and the second assumption is if MM is heteroidal, if any embedded I haven't defined this term, but incompressible torus is homotopic into boundary of M. So here the surface is said to be incompressible. So if you have a surface, this is a surface, and this is three manifold. So surface embedded in three manifold is said to be incompressible if the pi 1 of S injects to pi 1 of M. So by a homomorphism induced from the inclusion. Okay, so we impose the two conditions because if you have a hyperbolic metric, if interior of M has a hyperbolic metric, then M must be irreducible and heteroidal. So to generalize the product of the S and the interval, what you have to consider is such compact three manifold. So irreducible, heteroidal, orientable, compact three manifold. Okay. So for such a manifold, we are going to consider the same kind of thing. So we are going to define H of S, H of M, and AH of M, and the quasi-conformal deformation. Well, in this case, we don't have a function representation, so you have to choose some starting point to consider the quasi-conformal deformation space. But anyway, we know that exists, that starting point exists, and we can consider the quasi-conformal deformation space. So we can consider all the three. And it will turn out that, as in the case of the surface, so AH of M and H of M are the same. But QH of M, that is a generalization QF of S, so it's a quasi-conformal deformation space is smaller. And again, we will show that the closure of that, but closure of that is, well, it's a bit subtle, but closure of the union of quasi-conformal deformation space is the same as the entire deformation space or something like that. But anyway, so I should stop here today, and I will talk about that tomorrow.